A blast furnace is a type of metallurgical furnace used for smelting to produce industrial metals, generally iron, but also others such as lead or copper. In a blast furnace, fuel, ores, and flux are continuously supplied through the top of the furnace, while a hot blast of air is blown into the lower section of the furnace through a series of pipes called tuyeres, so that the chemical reactions take place throughout the furnace as the material moves downward. The end products are usually molten metal and slag phases tapped from the bottom, and flue gases exiting from the top of the furnace. The downward flow of the ore and flux in contact with an upflow of hot, carbon monoxide-rich combustion gases is a countercurrent exchange and chemical reaction process. In contrast, air furnaces are naturally aspirated, usually by the convection of hot gases in a chimney flue. According to this broad definition, bloomeries for iron, blowing houses for tin, and smelt mills for lead would be classified as blast furnaces. However, the term has usually been limited to those used for smelting iron or to produce pig iron, an intermediate material used in the production of commercial iron and steel, and the shaft furnaces used in combination with sinter plants in base metals smelting. History. Blast furnaces existed in China from about 1st century AD and in the West from the High Middle Ages. They spread from the region around Namur in Wallonia in the late 15th century, being introduced to England in 1491. The fuel used in these was invariably charcoal. The successful substitution of coke for charcoal is widely attributed to Abraham Darby in 1709. The efficiency of the process was further enhanced by the practice of preheating the combustion air, patented by James Beaumont Nielsen in 1828. China. The oldest extant blast furnaces were built during the Han Dynasty of China in the 1st century AD. However, cast iron farm tools and weapons were widespread in China by the 5th century BC, while 3rd century BC iron smelters employed an average workforce of over 200 men. These early furnaces had clay walls and used phosphorus containing minerals as a flux. The effectiveness of the Chinese blast furnace was enhanced during this period by the engineer Du Shi, who applied the power of water wheels to piston bellows in forging cast iron. While it was long thought that the Chinese had developed the blast furnace and cast iron as the first method of iron production, Donald Wagner has published a more recent paper that supersedes some of the statements in the earlier work. The newer paper still places the date of the first cast iron artifacts at the 5th and 4th centuries BC, but also provides evidence of earlier bloomery furnace use, which migrated from China to western parts and Central Asia during the beginning of the Chinese Bronze Age of the late Longshan culture. He suggests that early blast furnace and cast iron production evolved from furnaces used to melt bronze. Certainly, though iron was essential to military success by the time the state of Qin had unified China, usage of the blast and cupola furnace remained widespread during the Song and Tang dynasties. By the 11th century AD, the Song dynasty Chinese iron industry made a remarkable switch of resources from charcoal to bituminous coal in casting iron and steel, sparing thousands of acres of woodland from felling. This may have happened as early as the 4th century AD. The Chinese blast furnace remained in use well until the 20th century. The backyard furnaces favored by Mao Zedong during the Great Leap Forward were of this type. In the regions with strong traditions of metallurgy, the steel production actually increased during this period. In the regions where there was no tradition of steel making, or where the iron masters, knowing the traditional skills of the scientific principles of the blast furnace process, had been killed, the results were less than satisfactory. Elsewhere in the ancient world, in most places in the world other than in China, there is no evidence of the use of the blast furnace. Instead, iron was made by direct reduction in bloomeries. The bloomery process was invented probably in modern-day Xinjiang or other parts of western China by Hans or Mongols around 800 BC. Iron finds in China proper a few before bloomeries were supplanted by the blast furnace in the 5th century BC, which seems to have developed independently in the southern Chinese cultural sphere. An exception would be the Haya people of northwestern Tanzania, who are renowned for creating steel using a blast furnace process and refining process very similar to open hearth process for possibly as long as 2,000 years. In Europe, the Greeks, Celts, Romans, and Carthaginians all used this process. Several examples have been found in France, and materials found in Tunisia suggest they were used there as well as in Antioch during the Hellenistic period. Though little is known of it during the Dark Ages, the process probably continued in use. Similarly, smelting in bloomery-type furnaces in West Africa and forging for tools appear in the Nok culture in Africa by 500 BC. The earliest records of bloomery-type furnaces in East Africa are discoveries of smelted iron and carbon in Nubia and Axum that date back between 1500 BCE, particularly in Meroe. There are known to have been ancient bloomeries that produced metal tools for the Nubians and Kushites and produced surplus for their economy. Bloomeries have also been discovered and recorded to have been created in medieval West Africa with some of the metalworking Bantu civilizations, such as the Bunyoro Empire and the Nyoro people. Medieval Europe Catalan forges. The simplest forge, known as the Corsican, was used prior to the advent of Christianity. Examples of improved bloomeries of the stucco fan of the Catalan forge, which remained until the beginning of the 19th century. The Catalan forge was invented in Catalonia, Spain, during the 8th century. Instead of using natural draft, air was pumped in by a trompe, resulting in better quality iron and an increased capacity. This pumping of airstream in with bellows is known as cold blast, and it increases the fuel efficiency of the bloomery and improves yield. The Catalan forges can also be built bigger than natural draft bloomeries. Modern experimental archaeology and history reenactment have shown there is only a very short step from the Catalan forge to the true blast furnace, where the iron is gained as pig iron in liquid phase. Usually, obtaining the iron in liquid phase is actually undesired, and the temperature is intentionally kept below the melting point of iron, since while removing the solid bloom mechanically is tedious and means batch process instead of continuous process, it is almost pure iron and can be worked immediately. On the other hand, pig iron is the eutectic mixture of carbon and iron and needs to be decarburized to produce steel or wrought iron, which was extremely tedious in the Middle Ages. Oldest European blast furnaces. The oldest known blast furnaces in the West were built in Durstel in Switzerland, the Märkische Sauerland in Germany, and at Lafiten in Sweden, where the complex was active between 1205 and 1300. At Norra Skog in the Swedish parish of Jarnboas, there have also been found traces of blast furnaces dated even earlier, possibly to around 1100. These early blast furnaces, like the Chinese examples, were very inefficient compared to those used today. The iron from the Lafiten complex was used to produce balls of wrought iron known as osmonds, and these were traded internationally. A possible reference occurs in a treaty with Novgorod from 1203 and several certain references in accounts of English customs from the 1250s and 1320s. Other furnaces of the 13th to 15th centuries have been identified in Westphalia. The technology of blast furnace may have either been transferred from China, or may have been an indigenous innovation. Al-Qazvini in the 13th century and other travelers subsequently noted an iron industry in the Alborz Mountains to the south of the Caspian Sea. This is close to the Silk Route, so that the use of technology derived from China is conceivable. Much later descriptions record blast furnaces about 3 meters high. As the Varangian Rus people from Scandinavia traded with the Caspian using the Volga trade route, it is possible that the technology reached Sweden by this means. High-quality oars, water power for bellows for blast and wood for charcoal are readily obtainable in Sweden. However, since blast furnace has also been invented independently in Africa by the Haya people, it is more likely the process has been invented in Scandinavia independently. The step from bloomery to true blast furnace is not big, simply just building a bigger furnace and using bigger bellows to increase the volume of the blast, and hence the amount of oxygen leads inevitably into higher temperatures. Bloom melting into liquid iron and cast iron flowing from the smelters. Already the Vikings are known to have used double bellows, which greatly increases the volumetric flow of the blast. This Caspian region may also separately be the technological source for it. Furnace at Ferriere, described by Philaret. Water-powered bellows at Semogo in northern Italy in 1226 in a two-stage process. In this, the molten iron was tapped twice a day into water, thereby granulating it. Cistercian contributions. One means by which certain technological advances were transmitted within Europe was a result of the general chapter of the Cistercian monks. This may have included the blast furnace, as the Cistercians are known to have been skilled metallurgists. According to Jean Gimpel, the high level of industrial technology facilitated the diffusion of new techniques. Every monastery had a model factory, often as large as the church and only several feet away, and water power drove the machinery of the various industries located on its floor. Iron ore deposits were often donated to the monks along with forges to extract the iron, and within time surpluses were being offered for sale. The Cistercians became the leading iron producers in Champagne, France, from the mid-13th century to the 17th century, also using the phosphate-rich slag from the furnaces as an agricultural fertilizer. Archaeologists are still discovering the extent of Cistercian technology. At Lascaux, an outstation of Rievaulx Abbey and the only medieval blast furnace so far identified in Britain, the slag produced was low in iron content. Slag from other furnaces of the time contained a substantial concentration of iron, whereas Lascaux is believed to have produced cast iron quite efficiently. Its date is not yet clear, but it probably did not survive until Henry VIII's dissolution of the monasteries in the late 1530s, as an agreement concerning the Smythes with the Earl of Rutland in 1541 refers to blooms. Nevertheless, the means by which the blast furnace spread in medieval Europe has not finally been determined. Origin and spread of early modern blast furnaces. The direct ancestor of these used in France and England was in the Namur region in what is now Wallonia. For there, they spread first to the Pays de Bray on the eastern boundary of Normandy, and from there to the Weald of Sussex, where the first furnace in Buxted was built in about 1491, followed by one at Newbridge in Ashdown Forest in 1496. They remained few in number until about 1530, but many were built in the following decades. In the Weald, where the iron industry perhaps reached its peak about 1590, most of the pig iron from these furnaces was taken to finery forges for the production of bar iron. The first British furnaces outside the Weald appeared during the 1550s, and many were built in the remainder of that century and the following ones. The output of the industry probably peaked about 1620, and was followed by a slow decline until the early 18th century. This was apparently because it was more economic to import iron from Sweden and elsewhere than to make it in some more remote British locations. Charcoal that was economically available to the industry was probably being consumed as fast as the wood to make it grew. The Back Barrow blast furnace, built in Cumbria in 1711, has been described as the first efficient example. The first blast furnace in Russia opened in 1637 near Tula and was called the Gorodishchi Works. The blast furnace spread from here to the central Russia and then finally to the Urals. Coke blast furnaces in 1709 at Coalbrookdale in Shropshire, England. Abraham Darby began to fuel a blast furnace with coke instead of charcoal. Coke's initial advantage was its lower cost, mainly because making coke required much less labor than cutting trees and making charcoal. But using coke also overcame a localized shortages of wood, especially in Britain and on the continent. Metallurgical grade coke will bear heavier weight than charcoal, allowing larger furnaces. A disadvantage is that coke contains more impurities than charcoal, with sulfur being especially detrimental to the iron's quality. Coke iron was initially only used for foundry work, making pots and other cast iron goods. Foundry work was a minor branch of the industry, but Darby's son built a new furnace at nearby Horsehay, and began to supply the owners of finery forges with coke pig iron for the production of bar iron. Coke pig iron was by this time cheaper to produce than charcoal pig iron. The use of a coal-derived fuel in the iron industry was a key factor in the British Industrial Revolution. Darby's original blast furnace has been archaeologically excavated and can be seen in situ at Coalbrookdale, part of the Iron Bridge Gorge Museums. Cast iron from the furnace was used to make girders for the world's first iron bridge in 1779. The iron bridge crosses the River Severn at Coalbrookdale and remains in use for pedestrians. Hot blast. Hot blast was the single most important advance in fuel efficiency of the blast furnace and was one of the most important technologies developed. During the Industrial Revolution, hot blast was patented by James Beaumont Neilson at Wilsontown Iron Works in Scotland in 1828. Within a few years of the introduction, hot blast was developed to the point where fuel consumption was cut by 1/3 using coke and 2/3 using coal, while furnace capacity was also significantly increased. Within a few decades, the practice was to have a stove as large as the furnace next to it, into which the waste gas from the furnace was directed and burned. The resultant heat was used to preheat the air blown into the furnace. Hot blast enabled the use of raw anthracite coal, which was difficult to light, to the blast furnace. Anthracite was first tried successfully by George Crane at Innes Edwin Iron Works in South Wales in 1837. It was taken up in America by the Lehigh Crane Iron Company at Catasauqua, Pennsylvania in 1839. Modern furnaces. Iron blast furnaces. The blast furnace remains an important part of modern iron production. Modern furnaces are highly efficient, including copper stoves to preheat the blast air and employ recovery systems to extract the heat from the hot gases exiting the furnace. Competition in industry drives higher production rates. The largest blast furnaces have a volume around 5,580 cubic meters and can produce around 80,000 tons of iron per week. This is a great increase increase from the typical 18th-century furnaces, which averaged about 360 tons per year. Variations of the blast furnace, such as the Swedish electric blast furnace, have been developed in countries which have no native coal resources. Lead blast furnaces. Blast furnaces are currently rarely used in copper smelting, but modern lead smelting blast furnaces are much shorter than iron blast furnaces and are rectangular in shape. The overall shaft height is around 5 to 6 meters. Modern lead blast furnaces are constructed using water-cooled steel or copper jackets for the walls, and have no refractory linings in the side walls. The base of the furnace is a hearth of refractory material. Lead blast furnaces are often open-topped rather than having the charging bell used in iron blast furnaces. The blast furnace used at the Nystar Port Pirie lead smelter differs from most other lead blast furnaces in that it has a double row of tuyeres, rather than the single row normally used. The lower shaft of the furnace has a chair shape with the lower part of the shaft being narrower than the upper, the lower row of tuyeres being located in the narrow part of the shaft. This allows the upper part of the shaft to be wider than the standard zinc blast furnaces. The blast furnaces used in the imperial smelting process were developed from the standard lead blast furnace, but are fully sealed. This is because the zinc produced by these furnaces is recovered as metal from the vapor phase, and the presence of oxygen in the off gas would result in the formation of zinc oxide. Blast furnaces used in the ISP have a more intense operation than standard lead blast furnaces, with higher air blast rates per square meter of hearth area and a higher coke consumption. Zinc production with the ISP is more expensive than with electrolytic zinc plants, so several smelters operating this technology have closed in recent years. However, ISP furnaces have the advantage of being able to treat zinc concentrates containing higher levels of lead than can electrolytic zinc plants. Modern process. Modern furnaces are equipped with an array of supporting facilities to increase efficiency, such as ore storage yards where barges are unloaded. The raw materials are transferred to the stockhouse complex by ore bridges, or rail hoppers and ore transfer cars. Rail-mounted scale cars are computer-controlled weight hoppers weigh out the various raw materials to yield the desired hot metal and slag chemistry. The raw materials are brought to the top of the blast furnace via a skip car powered by winches or conveyor belts. There are different ways in which the raw materials are charged into the blast furnace. Some blast furnaces use a double bell system where two bells are used to control the entry of raw material into the blast furnace. The purpose of the two bells is to minimize the loss of hot gases in the blast furnace. First, the raw materials are emptied into the upper of small bell, which then opens to empty the charge into the large bell. The small bell then closes to seal the blast furnace, while the large bell rotates to provide specific distribution of materials before dispensing the charge into the blast furnace. A more recent design is to use a bell-less system. These systems use multiple hoppers to contain each raw material, which is then discharged into the blast furnace through valves. These valves are more accurate at controlling how much of each constituent is added as compared to the skipper conveyor system, thereby increasing the efficiency of the furnace. Some of these bell-less systems also implement a discharge chute in the throat of the furnace in order to precisely control where the charge is placed. The iron-making blast furnace itself is built in the form of a tall structure lined with refractory brick, and profiled to allow for expansion of the charged materials as they heat during the descent, and subsequent reduction in size as melting starts to occur. Coke, limestone flux, and iron ore are charged into the top of the furnace in a precise filling order which helps control gas flow and the chemical reactions inside the furnace. 4. Uptakes allow the hot dirty gas high in carbon monoxide content to exit the furnace throat, while bleeder valves protect the top of the furnace from sudden gas pressure surges. The coarse particles in the exhaust gas settle in the dust catcher and are dumped into a railroad car or truck for disposal, while the gas itself flows through a venturi scrubber and/or electrostatic precipitators and a gas cooler to reduce the temperature of the cleaned gas. The cast house at the bottom half of the furnace contains the bustle pipe, water-cooled copper tuyeres and the equipment for casting the liquid iron and slag. Once a tap hole is drilled through the refractory clay plug, liquid iron and slag flow down a trough through a skimmer opening, separating the iron and slag. Modern, larger blast furnaces may have as many as 4 tap holes and 2 cast houses. Once the pig iron and slag has been tapped, the tap hole is again plugged with refractory clay. The tuyeres are used to implement a hot blast, which is used to increase the efficiency of the blast furnace. The hot blast is directed into the furnace through water-cooled copper nozzles called tuyeres near the base. The hot blast temperature can be from 900 degrees Celsius to 1300 degrees Celsius depending on the stove design and condition. The temperatures they deal with may be 2000 degrees Celsius to 2300 degrees Celsius. Oil, tar, natural gas, powdered coal and oxygen can also be injected into the furnace at tuyer level to combine with the coke to release additional energy and increase the percentage of reducing gases present, which is necessary to increase productivity.